Okay, so let's continue our discussion. We have already solved the first two exercises where we proved two results in this section. But now we should address some issues that we have already come across in this section. And that's why we have this why exercise. This of course is not there in the text. I have made it up to address those issues. So let's see what this is about. So here we have a set. Let X be a set. X is any type of set. X can be finite or infinite. And when X is infinite, it can either be countable or uncountable. And as usual, f is a real valued function defined on X, that is, f has X as its domain and R as its range. Now, the first thing we want to prove is when this sum of all the f values as X varies over X is absolutely convergent by the second definition of absolute convergence, which is the bigger one, the extension of the first definition, of course, because X is arbitrary, so X may very well be uncountable also. In such a situation, the first definition is it does not apply. So that's why by definition 824, if by this definition this is absolutely convergent, then this series is also absolutely convergent, where again we are considering the f values but only the non-zero f values. But have we not already proved this? The answer is no. The author just remarked that this should be true, or clearly when this is absolutely convergent, then so is this. Why? Because it's easy to believe, no? I mean, without being too rigorous, if you just simply casually think of this sum, then it is the sum of all the f values. And this one is the sum of all the non-zero f values. So they should naturally be equal, because anyway, when you are considering such a sum, the zero f values are not going to affect the sum. But that is just a vague understanding of what should be true. Is it really true? For that we need to prove that yes, when this is absolutely convergent, then this is also absolutely convergent rigorously. We have, however, proved one thing in, I think if I am remembering it correctly, lemma 8 to 5. In lemma 8 to 5, we proved that when this is absolutely convergent, then this set, the set of elements of X at which f does not vanish, is at most countable. This is something we have proved. And this in fact gave us an idea to define the value of this sum when it is absolutely convergent to be the value of this sum, which is already available, and that comes from definition 821. Why? Why is that justified? Because the set over which you are considering the sum is at most countable. So that's how we define the value of this sum when it is absolutely convergent. But we have not proved that this series is also in that case absolutely convergent. So that is one thing we want to do. And the second thing is this: why is this new definition, that is definition 824, consistent with the old definition 821? What do we mean by this consistency? That is just simply this. Say you consider this sum again with all these hypotheses, but now X is at most countable. Then you can define this sum in two ways, either using the first definition or using the second definition. Consistency of the two definitions means that when this is absolutely convergent by the first one, then it should also be absolutely convergent by the second one, and vice versa. When it is absolutely convergent according to this second definition, it should also be absolutely convergent according to the first definition. And that is something actually we have proved. We will see, but then what is left for us to do? That is because in this case, say it is absolutely convergent under either definition and hence by both the definitions, but still something is still there for us to prove. So when the series or the sum is absolutely convergent, it will converge to something, it will have a value, right? And that value itself has two definitions. See, when x is at most countable, let us consider the two cases. Say x is finite, then this is a finite series, and we already know what the value would be. It will just simply be the sum of all the f values. Since there are finitely many such f values, so that sum is already there. And when x is countable, then the value of this comes from this definition. And what is that value? That value is just this, because this is absolutely convergent by this definition and also by this definition, but right now we are looking at the consequence of this definition. So what does this definition say? It says that there exists a bijection like this, for which this infinite series itself is absolutely convergent, and it will have some sum, and that sum is the value of this sum. That is one thing. But at the same time, if we apply this definition to find the value of this sum, it is slightly different. What is it? It goes like this. That is, the value of this sum at the same time, using definition 824, is the value of this sum and the value of this sum itself again comes from definition 821, just like this one. We are able to apply the first definition to the series itself because x is at most countable. But we can also apply this definition and instead work with this sum. This sum should also have that same value. That is not immediately clear. Okay, so these are the things we need to answer in the solution. So let us start the solution. So first we will prove this. Now this is absolutely convergent. We need to prove that this is absolutely convergent. So this is how we start. Since the set of those x at which f does not vanish is a subset of x, we have the following inclusion. this set is a subset of this next set. Okay, but how? Let's see. It's not that difficult, but still let's see exactly how. In order to prove that this set is a subset of this set, you take an arbitrary element of the first set. That arbitrary element is a finite sum, which looks like this, where A is a finite subset of this set. But since this set itself is a subset of X, so automatically that A would be a finite subset of X. So that sum would naturally belong to this set also. And that is how this is a subset of this. And now it has its consequence. What is our hypothesis? That this is absolutely convergent. So, if this is absolutely convergent, then first of all we note this. We write the consequence, or rather the definition of absolute convergence of this. It means that the supremum of this set is less than infinity, by definition 824. Just give me a moment. That is supremum of this set. A is finite. Okay. Now look at the fact that this set is a subset of this set. And supremum means what? Least upper bound. So the least upper bound is after all an upper bound also for this set. That means all the elements of this set are going to be less than or equal to this supremum. In particular, all the elements of this set also then are going to be less than or equal to this supremum, because these elements also belong to this set, since it's a subset of this set. And that is why this supremum will be an upper bound for this set as well. So then can we say something about the least upper bound of this set? This is one upper bound of this set. So the least upper bound of this set will be less than or equal to this, which is some upper bound. So that's why this is greater than or equal to the supremum of this set. Where A is a subset of the set of non-vanishing, those points at which F does not vanish, and A is finite. But that just tells us what? It tells us that this series is absolutely convergent. Is absolutely. Why is the ink not coming properly? So that was the first thing we wanted to prove. And if you look at this whole argument, the specific nature of this set has actually played no role in this argument. The only thing that we used is that this is a subset of capital X. That means the same argument will apply to actually any subset of capital X. So that's why next we just write that observation down. It will be useful later on. In general, for any such subset of X, this is absolutely convergent if this is so. Okay, naturally. And next we come to the question of consistency of the two definitions. Although we already know, like how I was saying there, that the series is absolutely convergent under one definition if and only if it is absolutely convergent under the other one. But we need to mention exactly what result supports that fact. And that result is it lemma or proposition? Lemma. We know from lemma 8 to 3 that okay. Now I cannot just directly write like this. I need to first of all assume that X is at most countable, because otherwise applying definition 8 to 1 to see whether this is absolutely convergent or not may be meaningless, because X may not be at most countable. So I need to assume that this is at most countable. Yeah, now we can write. We know from lemma 8 to 3 that this is absolutely convergent by definition 8 to 4 if and only if it is so by definition 8 to 1. But let us also remember that subtle fact that x is at most countable, and in fact when we were going through the solutions to the first two exercises in the previous video, we noted that definition 8 to 1 does not exactly cover the case when x is a finite set. So we needed to extend this slightly in order to include that case where x can be a finite set. So that's why within brackets we write like this. It's not exactly definition 8 to 1 we are talking about, but rather its slight extension, which talks not only about countable sets but about finite sets, sums over finite sets as well. In fact, its slight extension means the extension of the first definition of absolute convergence, which we can see in the solution to the first exercise. Okay, so that is just simply a matter of putting things in a rigorous manner and just stating what we already know. But now we have that issue of when we have absolute convergence, what about the sum? What about the value of the sum? Do we have the same value under both the definitions? That's what we are going to next. Okay. So let us do that in the next paragraph. So again, just to emphasize the fact what we are doing, what our hypotheses are. Again we write let x be at most countable and the sum be absolutely convergent. Now it does not matter under what definition because of the previous paragraph. We claim that this sum, or rather its value, is equal to the value of this sum, where y is this set. See, definition 8 to 4 assigns the value this to this sum. So by definition 8 to 4, if we are going, then the sum by that definition should have this value. However, because x is at most countable, this already has a value of its own which does not depend on definition 8 to 4. If x is finite, we know what this means. It's just a finite series, a finite sum. When x is countable, then its meaning comes from, or rather its value comes from definition 8 to 1. That is the first definition of absolute convergence. And now we want to prove that this sum is equal to this sum. So that's what we want to prove. Okay. So let's see what the cases are. If x is finite, then so is y, and the claim follows from properties of finite sums. So what we are saying is that when x is finite, then y is finite, of course, because y is after all a subset of x. But then we are dealing with finite sums on both sides of the equality sign, and it follows from elementary property or from properties of such finite sums that these two are equal. And why is that so? That is because in this sum we are only considering the non-zero values of f, and here we are considering all values of f. And y is precisely the set of non-zero values of f. So the two sums should be equal. I mean, it's just simply a thing that you feel it should be true, but still actually needs to be proved. So that proof I leave to you. I won't even say what strategy you should use. You just come up with something on your own. So we leave this finite case behind and we move forward. Now let x be countable. So now x is infinite, and it is that means it's countable. Now under this case there are two cases depending on whether y itself is finite or countable. So we consider the finite case first. If y is finite, then one can prove that the sequence of partial sums of this series after turning it into an infinite series, that means an ordinary infinite series, by choosing a bijection from n into x. So what are we saying? If y is finite, then one can prove that the sequence of partial sums of this after turning it into an infinite series by choosing such a bijection is eventually constant with the constant being this. So now we need to understand what is it that we have written here. We have written quite a long sentence. What is the meaning of this? Okay. Now note that we are going to understand the meaning here, which is not a part of the solution. It's only for our understanding. So we put a line here and we try to understand the meaning of this. So now the situation is this: x is countable. Okay, so there will be some bijection between n and x, and because x is countable, the value of this sum by the first definition, that is 8 to 1, is this. Say you choose a bijection, say that bijection is G. Then the value of this sum should be the sum of this infinite series. And how do you find the sum of an infinite series? By seeing what the sequence of partial sums of that series converges to. So now you think of y. Y is finite. And what is y? Y is the set of those points in x at which f does not vanish. F vanishes everywhere else. So what type of sequence of partial sums can we expect from this situation? And what would be the sequence of partial sums of this? Its general term looks like this. This is the sequence of partial sums of this series. Now whatever real number this sequence converges to, that is the sum, that is the value of this. Okay. On the other hand, because here y is finite, we already know the value of this. It's just a sum of finitely many real numbers, f values. Now if you think of the terms of this sequence, you look at the first term. What will be the first term? The first term, since to get the first term you would have to put n equal to 0. So in that sum you will have only one term, and that is f of g of 0. What will happen to the second term? It will be f of g of 0 plus f of g of 1. Okay, so that is the second partial sum. And then you will have the third partial. Let me write one more. And it goes like this. So this sequence is just simply this sequence. Okay. Now, we don't really know precisely which of these f values are going to be non-zero. All we know is that the set of those points at which f does not vanish is y. And since y is a subset of x, so those points in y are going to appear among these gi's. This g of 0 may actually not be in y. It may be outside of, it is in x no doubt, but it may not be in y, and as such this f value may be 0. Maybe the next one belongs to y, so that f of g of 1 is a non-zero real number. Maybe the one after that is also non-zero. Okay. So it entirely depends on what the set y is, but because y is finite, the elements in y are going to be exhausted at some point in considering these partial sums. That is, if you take the sum long enough, because the number of terms is increasing by 1 every time you consider the next term, the next term, the next term. So you are considering also simultaneously these g values. So the g values are in fact elements in x, because g is a bijection from n into x. So as you are considering this g of 0, g of 1, g of 2, actually you are considering the elements of x. Now among those elements you have the elements of y, and that's why, because y is finite, this is going to exhaust all the elements of y eventually. And after that what happens? Say you consider a sum long enough, don't really know how many terms you have to add, but because y is finite, you will find an n, a natural number n so large that among all the gi's where I varies from 0 to n have all the y terms among them. Okay. But then if you continue still further, you continue to write even more partial sums. What are you going to get? See, you have run out of non-zero f values because you have run out of elements in y. Whatever elements in y, whatever the elements you have in y, they have already appeared among these g values. Nothing else is going to appear that is going to give you more non-zero f values. So at that stage the sum stalls. You will continue to get more terms in the sequence of partial sums. Since it's a sequence, you will, even after having this, you will continue to get infinitely many more terms, but all of them are going to have the same value as this. Why? That is because the next f values, that is g of f of gn plus 1, will be 0, because gn plus 1 does not belong to y. We already have exhausted all the y values. F of gn plus 2 is also 0. So adding those extra things and thereby getting the next partial sum, the one after that, the one after that, they are also, all of them are going to be equal to this. And because only the non-zero values of f, all the non-zero values of f are in fact coming from y. So that's why eventually this sequence of partial sum is going to be constant. After some stage, its terms are going to be the same, and naturally that sum will be this. So that's what we have written, that if y is finite but x is countable, then the sequence of partial sums of this series after turning this sum into an infinite series by choosing such a bijection is going to be eventually constant, and that constant being this. So according to the definition of the sum of an infinite series, this will converge to what? Since it's an eventually constant sequence, it will converge to that constant, and that constant is this. So the sum of this series is this, but the sum of this series by definition is the value of this sum. So that's why this is equal to this. So how shall I write it after this? So I can just simply write directly. So we understand how this is true when x is countable but y is finite. And now we are going to look at the last case where y is also countable. Okay. Now let y be also countable, that is, besides x, y is also countable. Now what is the meaning of our sums? Let's see that. These parts in between these horizontal lines are not parts of the solution. I am writing, the things I am writing in them are for our understanding only. So one of the sums is this. I need more space. No? One of the sums is this, and the other sum is this. And do not forget that this is given to be absolutely convergent, but this is absolutely convergent by what we proved in the beginning of this solution. And also don't forget what the set y is. Y is the set of those elements in X where f does not vanish. So according to the, so now X is countable, Y is also countable. So the values of this sums are going to come from definition 8 to 1, the first one. That means we should choose a bijection from n into x, say G1, and say you choose a bijection from n into y. In fact, it does not matter what bijections you choose, and the given sums using these bijections will turn into these infinite series. The sums of these infinite series are the values of these two sums respectively, and we want to prove that they are equal. Now everything depends on us cleverly choosing this G1 and G2, okay, which will show that these two sums actually are equal. In fact, as I have just now said, this is the value of this, this is the value of this, and those values are fixed and in fact do not depend on our choice of G1 and G2. That we already know. That is the idea of absolute convergence, right? But to show that these two values are equal, we need to choose G1 and G2 in a manner that there is a relation which will allow us to show that they are equal. Okay, so now we try to see what we can do for that. So we proceed like this. For G1 we are just simply going to choose any bijection, but then we will choose G2 depending on that choice of G1. Choose any bijection, say sigma, from n into x, and define the sequence Sn y f of sigma of I, where I varies from 0 to n, for we need not even write for n belonging to n because that is understood. So here what we have done is that in place of G1 we are just simply writing sigma, and we are considering this sequence. This is the sequence of partial sums of this series, where in place of G1 you have sigma, and we are considering this sequence because we want to know what the value of this series is, or rather this one is, where you would have infinity here. Okay, but now note one thing, that y is a subset of x. So because y is a subset of x, it makes sense to consider the inverse image of y under sigma, which will itself be a subset of n, because y lies here inside of x. So sigma inverse of y will be a subset of the set of natural numbers. Note that and in fact, if we restrict sigma to the inverse image, then this function would itself be a bijection naturally, because sigma is 1 to 1 and onto. So this is a bijection. Okay, now our y is countable, keep that in mind. So because we have a bijection between y and sigma inverse of y, sigma inverse of y will also be countable. So this is countable. But it's not just any countable set, it's a countable subset of the set of natural numbers. And for such sets, we already know something from the part where we discussed finite series, finite sets actually. This is countable. Then there exists a bijection let me write it from there. So there exists a bijection tau from okay, this part is a little complicated. I should not make any mistakes. Yeah, naturally there would be a bijection tau from n into sigma inverse of okay, sigma inverse of y being countable and a bijection existing like this is, they are just the same thing, because that's what countability means. But we want to say something more. Not just such a bijection exists, but one that is increasing. And this fact comes from proposition 815. You remember that result where we proved that when you have an infinite subset of the set of natural numbers, then you can find an increasing bijection from the set of natural numbers to that set. And in fact, that increasing bijection is unique. Although we do not need the uniqueness here, but still, let's mention that. Okay, now look at these two functions. Tau maps n onto sigma inverse of y, and this sigma, not the original one, but this sigma maps sigma inverse of y onto y. So now we can compose tau and sigma. And because this is the bijection and this is also a bijection, so the composition will also be a bijection. So, and the composition will follow what order? Sigma composition tau. And that will be a function from n to this and this to y, that means n to y. If you somehow are always confused about how to decide this order, you think of how you are going to apply this function. If the function is this, then your input lies to the right of the function name, right? Say x. So that means you need to apply tau first to x. Does that make sense? Yes, because tau is the one that is going to take us from n to sigma inverse of y, and then that means tau of x belongs to what set? Belongs to this set, and then on that you can apply sigma, because this is the domain of sigma. So this makes sense, not the other one. Tau composition sigma does not make sense. Some authors, particularly algebraists, some of them like to write x on this side. There is a reason for that. Okay, that is not an arbitrary choice. For them, this same composition would be tau composition sigma. So that's why, while dealing with compositions, you should be absolutely clear which one of the two function notations are being used. We are using this notation, so that's why the composition looks like this. Okay, so now this is a bijection. So that G2 function that we were discussing back there, which will allow us to turn the y series, that is summation f of x as x varies over y, into an infinite series, that function we are going to take this one, because you see, we need a bijection from n into y, right? Let us consider this bijection. So the infinite series that we are going to get from this sum will be this infinite series, sigma composition tau of I, where I varies from 0 to infinity. It turns out that this will get the job done. Now we want to see where this series converges. So that for that we would have to consider its sequence of partial sums. That's the thing next we are considering. So define the sequence of partial sums of our original series. The one where the sum has been taken over x is this. And now we are going to define the sequence of partial sums for this one, which we are going to call Tn. Define Tn by f of sigma composition tau of I, where I varies from 0 to n. Now we cannot of course find an exact real number to which this will converge, simply because the quantities involved here are actually arbitrary. F is arbitrary. We don't really know what the function f is. But we need to somehow link the terms Sn of that sequence with the terms Tn of this sequence. And here we make a claim. And this is our claim. We now claim that Tn is equal to S tau n for all natural numbers n. And now we are going to prove this claim. This claim is the thing that will let us conclude that the two sequences Sn and Tn converge to the same limit. And we will prove this claim by induction, because it seems like that should be the natural thing to do. And we write, let me first write the actual sentence that I wrote when I first solved this exercise. And then we will try to understand what I have written. Since f of sigma composition tau, or should I, f of sigma of, this part is a little confusing. For all natural numbers I less than tau of 0, note that tau is increasing so T0 is f of let me be a little more explicit. Just simply if we use the definition of T, it becomes this. F of sigma composition tau of 0 that is f of sigma of tau of 0, and that can also be written as summation f of sigma of I, where I varies from 0 to tau of 0, which by the definition of Sn is S tau of 0, and that is the basis of our induction. Now I cannot continue after this without explaining this part, because by the time I will reach this, I will have to erase this. So let me draw a figure of what is going on, because we have two functions sigma and tau, and we have also considered their composition. So the situation has become somewhat complicated. So how should I draw a figure about this whole thing? It looks somewhat like this. This is our set of natural numbers, and this is x. Originally, sigma is a bijection from n onto x. So we have a function sigma, and then what do we have? We have the subset y of x, and we made y correspond with, I can write y here also, sigma inverse of y in a natural way using sigma itself, and this correspondence is also 1 to 1 and onto, that is, it's also a bijection. And you can now see in the figure clearly that this is a subset of n. But because y is countable, so this is also countable due to them being of the same cardinality, there would be a bijection between this and n again. For that, we draw another copy of n, and that function, that bijection between n and sigma inverse of y is our tau. And composing this sigma and tau, this sigma, not the entire sigma, and tau, we have got a bijection from n into y. So you can see that, we of course have to write things in words and using mathematical symbols, but the moment you draw a picture, everything you can see at once and it becomes very clear. But now we have to zoom in and see what is going on inside this intermediate n. Okay, so what is happening is this. This is our n, this is our n, this is n, this is also n, and on this side we have x, x. Now, if you this is after all the set of natural numbers now. So its elements already are ordered in their natural order, 0, 1, etc. It goes like this, 0, 1, 2, 3 and so on. It descends down indefinitely. Now, sigma inverse of y may not be the entire n, because it's after all just a subset of n. We don't really know whether it is equal to n or not. So likely some natural numbers will not belong to sigma inverse of y. But note that tau itself is a bijection from n into sigma inverse of y. So we have another way of ordering the elements of sigma inverse of y themselves, but there is a relationship between that ordering of the elements of sigma inverse of y which is created by tau and the natural ordering of all the elements of n y, and those two orderings are compatible with each other, and that fact comes from the property that tau is increasing. So that's why the elements of sigma inverse of y will appear among all the natural numbers in this way. Say these first few elements are not in sigma inverse of y, but then you encounter the first element of sigma inverse of y in the form of tau of 0, because tau is already giving an order to the elements in sigma inverse of y. Then maybe you miss some more elements of n in sigma inverse of y, but then you encounter the next element of sigma inverse of y. So the set sigma inverse of y in n as a subset looks like this, and it goes like that. It captures some elements, misses some other elements in between, possibly. Actually t of 0 may be equal to 0, we don't really know, but we have allowed for the possibility that there may be some time before an element is captured inside sigma inverse of y. Okay. Now this is x and this is y. So when we look at in n, of course we have our usual ordering. So when we look at the function sigma composition tau, 0 gets mapped to what? 0 gets mapped first to tau of 0 by tau, and then that tau of 0 it itself gets mapped by sigma to sigma composition tau of 0, which is an element here. Similarly, 1 gets mapped to this element, but then that gets mapped by sigma to sigma composition tau of 1, which is again an element in y, and this is a one-to-one correspondence. That's what we have written, right? Sigma composition tau is a bijection from n into y, and this bijection we have used to create that infinite series out of that summation f of x as x varies over y. And on these elements, actually we are applying the function f and getting real numbers. So only the elements in y contribute to non-zero values of f. The other elements outside of y which lie in x contribute 0, that is 0 f values. So that is why when we calculated t of 0, by definition is just this, which you understand is just this. Now when you are considering this sum, in this sum how would things start? F of sigma of 0. Sigma of 0 is this. Sigma of 0 is not an element in y. Y is sigma of 0 not an element in y. How am I able to suddenly say that sigma of 0 does not belong to y? It belongs to x, no doubt about that, because sigma takes us from n into x, but sigma of 0 does not belong to y because 0 does not belong to sigma inverse of y by the definition of inverse image, because these elements do not belong to sigma inverse. Don't forget that this toothbrush like structure, having infinitely many bristles, is actually sigma inverse of y. So unless you encounter tau of 0, you are not going to get an element in y. You will continue to get elements in x which are not in y. So all them, if you apply f, you are going to get zeros. Okay. So the only non-zero value, that f value that you are going to have in this sum is for I equal to tau of 0. So that's why you are having this s of tau of 0. And now I think it will be clear if I write the next line. So whatever we have claimed here has been proved for the case n equal to 0. That is the basis of our induction. Now we write the induction hypothesis. Assume that Tn is equal to S tau n for some natural number n. Again, since f of g of I is equal to 0 for all natural numbers I satisfying these inequalities, we have Tn plus 1. First we write what Tn plus 1 is. Sigma composition tau of I 0 to n plus 1. See, do not fall in the trap of skipping steps and feeling like you are being cool with mathematics. No, that's just simple stupidity. You should write as many things as you want, no matter how dumb that looks, because the ultimate aim is not to show how fast we can do something, but how well we can do something. Okay, so we look at this. So now this becomes what? Summation I equal to 0 to n f of sigma composition tau of I plus f of sigma, won't have space here, but let me continue like this, at n plus 1. Okay, so okay, in order to show that this sum is just this much, let me put brackets also. But this is what? This is Tn plus this. Now Tn is what? Tn is S tau n by our induction hypothesis, and in place of this single thing we can write summation f of sigma. Watch this. Okay, let's see if I can get it correctly. F of sigma of I, where I is varying from tau of n plus 1 to tau of n plus 1. We understand how this is equal to this. It's coming from our induction hypothesis. But what about this? You see, when you take the value I equal to tau n plus 1, if such I exists, if it does not exist, then fine. You after this tau n, you will directly get tau n plus 1. because tau n plus 1 in that case is equal to tau n plus 1. But if you have such i's in between, then you get tau n plus 1. But for such an I, the f of g of I is equal to 0. So until you reach tau of n plus 1, the f values are 0. So we have just simply written 0 values here, and the last term, when you take I equal to tau n plus 1, you get this single term. So that's why that last single term is in fact equal to this sum. And that's, now the entire thing becomes what? Now I can erase the figure, now that we have hopefully understood. This is equal to, it is now just a simple sum as I varies from 0 all the way up to tau n plus 1 without skipping anything in between. So this is equal to S tau n plus 1. You can see why, because S tau n, if you write that also as a sum, it will be summation of f of sigma of I as I varies from 0 to tau of n, and then you continue that with this and use one of those rules of finite sums, finite series. That entire thing will be summation f of sigma of I, where I varies from 0 to tau of n plus 1, which is by definition of Sn S tau n plus 1. Let's see. That's what we wanted to show. So this is our induction step. This completes the induction, or you can write in short. So by induction and establishes our claim. So we have proved our claim. Now shall we go back to the claim and let's see what it really tells us about the relationship between the sequence Tn and the sequence Sn. Note that our tau is not just a bijection, it is actually an increasing function, and that fact, along with these equations, it's not a single equation of course, there are infinitely many equations when you change the value of n. The fact that tau is increasing and these equations together tell us what? That this is a subsequence of this sequence. We know that this is convergent, so because this is a subsequence of this will also be convergent and will have the same limit. And those two limits, the limit of this is the sum where the set is x, and the limit of this is the sum where the set is y. That's it. So Tn is a subsequence of Sn. All of these things look so complicated, but the intuition is really easy. It's like you are when you encounter the y, the elements in y, and you include them in your f values in the partial sum for the first series where the thing varies over x. Only those y values contribute anything to the sum. The intermediate x values which contribute 0 to the sum actually ultimately do not contribute anything. So they should in fact converge to the same real number. But in order to make that rigorous, we have had to do so much. So it's one thing to have an intuition, but to put it into words and so that you can see that yes, it is true, that is another thing. So this is a subsequence of this, and in brackets we also write, note that the increasing nature of tau is essential for this conclusion. Hence, we can finally conclude and end the solution like this. This is the limit of Sn, but that is also equal to the limit of Tn, which is the sum of the f values as the independent variable varies over y, and this completes the whole thing. But we would like to actually do a little more still. Lastly, we claim that if you have a set trapped in between y and x, like this, then how would you conclude this? We are doing all these extra things so that we can use them later when the need arises. The need will arise, okay? Now, but what is the premise of this? What are our hypotheses? Again, same thing. This is absolutely convergent. And y is that set? The set of those x where f does not vanish. And z is some subset satisfying which lies in between y and x. So we already know that this is absolutely convergent. How? You go back to the end of the first paragraph in this solution. There we dealt with that thing, no? Where we said that the set z, if z is any subset of x, then the corresponding sum is absolutely convergent if this one is absolutely convergent. So that's why we had that back there. Okay, now since y is a subset of z or z, What is y? Y is the set of those points where f does not vanish. But if set of those points in x where f does not vanish, but because y is given to be a subset of z already, so naturally we would have this. That is because the elements in x which give us non-zero f values all already belong to z due to this inclusion. So y in fact is also equal to this. Hence this, that is the status of y as a subset of x being the set of those elements where f does not vanish, is also the status of y as a subset of z. That is, for the set x we have the set y, so for the set z also that similar set is y. And we have already proved that when this is absolutely convergent, not only is this absolutely convergent, but the sums are same. So that from that we have this, but also we already have this. So that finally ends our solution. Okay, so whatever confusions we probably had about all these issues, now they are gone. And now in the next analysis video we are going to continue solving the other exercises that come after the second one. And that's just it for tonight, and tomorrow we have an upload. Actually I was supposed to upload this yesterday, but something happened, I wasn't able to do it. But anyway, tomorrow we have an upload, and let's do number theory again, after which we will do graph theory. So that's just it. So see you tomorrow with number theory. Until then, this is me, Lucifer, from A Mathematical Truth. Have a nice night.